Okay, welcome back to our class. So today we'll spend some time reviewing some of the key concepts that you should pay attention to before your final assessment. So just to remind you of the exam format, it will be on the 12th of December. Is that Monday or Tuesday? Anyways, it's on the 12th of December. It'll be 3 hours in person. I think it's at one of the sport facilities. Anyhow, it's in person, 3 hours, and there are 3 questions. Just like any standard exam, it should be out of 100 marks. It's closed book, so it's quite different than during the pandemic days. So you need to prepare for it, just like an old exam. There are some key points. You can of course use calculators. You don't need to memorize any equations because I'll provide you with all the necessary equations. I'm not going to define each variable. I think you should know what the variables are if you studied. So I'm not going to give you the units or the variables. Not that it's going to be very confusing, but you don't need to memorize any equations, is the key point. Where possible, try to state all assumptions that you've made so that we can understand your thought process when we're marking your exam. And to help you to better illustrate your thoughts or your concepts, please try to use schematic diagrams or graphs where necessary. So it's nothing unique here. We're following a typical written exam. There will be 2 types of questions. They're worth 50 marks each. We have conceptual questions, and then we have calculation questions. Conceptual questions will not require you to write long, eloquent essays or paragraphs even. The key of the conceptual questions is to see if you understand the key points. So if you write down the key words, the key concepts, that will be enough for you to get the marks. So please try not to be long-winded. Sometimes if you're long-winded, it can backfire, right? Because you start writing things that contradict yourself. So try to be clear and concise, hit the keywords. A lot of the students in past years, I think they panic a bit, but I think the key is to remain calm. Look at the number of marks stated for each question. If it says 3 marks and you only write 1 concept, then you know there's probably something wrong. These slides are posted on Moodle, by the way. I saw some of you taking pictures. Yeah, so stay calm and always count the marks. And another strategy is when you count the marks, I'm not sure how you prefer to take exams, but normally I look at which questions are worth the most marks, which ones I can get with a lot of confidence, and I try to finish those off first. So it's nice to just take a quick look at the exam overall before you start your paper. And also, I think over recent years, especially during the pandemic, I think it was very difficult for students as well. And I remember in other courses, not so much mine, a lot of students didn't even attempt any questions. That can be quite dangerous. I think you should try to attempt all questions. And by attempt, why not just list some assumptions, list some key formula, describe the process, how you would solve it. It may not necessarily matter if you can't get the correct answer, but it actually hurts a lot to leave a question blank, especially if the exam person marking the exam is feeling generous with the grades. But if you write nothing, there's nothing the examiner can do to help you, right? If you write something, then you help yourself. Well, you have to write something pertinent, right? You cannot draw a picture of something that's irrelevant, but it must be pertinent to the question. So please try to attempt all questions, right? That's why it's listed twice for the conceptual and calculation questions. Attempt all questions. For the calculation questions, under pressure, I entirely understand you may not get the correct mathematical answer, but that happens, right? But you should at least draw all your steps clearly. And even if you make an error in calculation or mathematics, that's okay, as long as you explain the concept. And like you said, there might be more than one way to solve a question. So you may need to guide us as we look through it. For some calculation questions, you can even list assumptions if necessary. Show the governing equation as we mentioned, and if you need, use a free body diagram, use graphs, draw whatever you need to express yourself more clearly. So these are the two main types of questions you face, worth 50 each. So it's good to spend a bit of time understanding concepts and different approaches to calculate questions. You can also probably surmise that if we didn't spend too much time on a particular topic in our class, I don't think it would make sense if I loaded the exam with those types of questions. So based on what we worked together in class, you can probably be comfortable enough to focus on those aspects. So in terms of concepts in each topic, let me go over a few key concepts for you to review at least. The first module we looked at for ground improvement was compaction. There were two types of compaction, if you recall, shallow and deep. For shallow compaction, we spent some time looking at Proctor testing. So it'd be nice to review the typical procedure for Proctor testing. Also look at what the soil mechanism is when we're talking about trying to expel the poor air phase. We treat it as a three-phase soil. Understand the procedure, 3 lifts, 25 blows, standard hammer, standard Proctor mode. And most importantly, perhaps for a calculation question, it might be easy grade, easy marks if we just ask you to plot out the Proctor curve, plot out the zero error void line. If you can do these, I think these are perhaps easy marks, right, for interpreting Proctor test results. And also, you should understand, of course, the advantages and limitations of the Proctor test. Under what circumstances we would use a Proctor test. Under what circumstances a Proctor test, at least the standard one, may not work so well. So these are some of the features you need to look at when you're reviewing the compaction module. Another aspect of shallow compaction that we looked at was related to quality control. There are 3 main quality control methods, if you recall. The sand cone replacement test, then we also have the rubber balloon method, which is method-wise and concept-wise more or less the same as the sand replacement test. If you understand the sand replacement test, there should be no problem with the rubber balloon, because you're essentially digging a hole and trying to find the volume of that hole to deduce the dry density. We also mentioned that there's something called a nuclear gauge. Although the concepts are more complex, at least you should understand for each of these 3 quality control methods for shallow compaction, what are the advantages, what are the disadvantages for these approaches. Related to compaction, how does it happen in the field? What type of plants and equipment do we use? When is it beneficial to use a particular plant over another? More importantly, how do we use relative degree of compaction or degree of compaction? How does it link between field and lab? You should understand the physical meaning of the degree of compaction. Can it be larger than 100%? If it is, what does it mean? If it's substantially lower, what does it mean as well? You should also be able to recommend something. If I gave you a scenario and asked you which QA or quality control test or quality assurance test we should use, you should be able to recommend the most suitable one. You should also be able to recommend the most suitable plant for compaction as well. If you remember, there's a sheep's foot roller for adhesive soils, and anything with granular compositions, you probably want to use a vibratory device, right? So these should be quite automatic in your minds. And of course, you should be able to work through a sand cone replacement test. We did an example in class, but we can't really make these more complicated than that. So if you understand how to calculate the dry density of in situ soil after you dig a hole, that's perhaps enough. And if I tried to change it into a rubber balloon question, if you understand the concept for a sand replacement test, it would be exactly the same. Only one, you're putting a fluid membrane in, and the other, you're putting sand in. So that's all you should understand for quality control or shallow compaction. Near the latter part of the first module, compaction, we discussed deep compaction, and over the course you would have realized that there were overlapping elements in the other types of ground improvement that was also very similar to deep compaction. For example, some of the deep mixing approaches or deep replacement approaches were somehow compacting soil as well. So there were some overlaps that if you notice them, it might be quite useful for you, right? For deep compaction, you have to be able to understand what the fundamental differences are of shallow and deep compaction. When would you recommend either approach? How do we do quality control of both approaches? Evidently, we just talked about the 3 sand replacement tests, rubber balloon tests, nuclear densometer tests for shallow, but can we do the same thing for deep compaction, or should we use something else? If I give you a scenario on a site, maybe you can tell me which compaction method I should use. And in order to do that, you have to be able to reveal what are the disadvantages and advantages of both approaches. Conceptually, there are 2 deep compaction methods, particularly dynamic compaction, where we're dropping a heavy weight on, and also vibro compaction. You should be able to explain, at least conceptually, what are we trying to do in the soil with these 2 approaches, and that's all you probably have to study pertaining to deep compaction. And then we moved on to perhaps one of the most important modules related to consolidation. It's quite easy to give written questions for consolidation, so please spend more time trying to understand the fundamentals of consolidation. Now, even though consolidation was a single module, we broke it up into several core components. Let me talk about these components. We talked about odometer testing. Conceptually, what's the difference between drain and undrained loading? Can you explain what's happening to the soil in terms of soil mechanics fundamentally? What's the mechanism for consolidation? So this is something you probably learned during your second year soil mechanics class. And then, can you compare consolidation with compaction? What are the fundamental differences? How do we conduct an odometer test? Can you discuss the procedure? And although we didn't go in a lot of detail, this is somehow a review of your soil mechanics class days. And then if you look at an odometer test result, can you explain what's happening in terms of the phases? Is this primary consolidation? Is this secondary consolidation? What's happening based on this dial gauge reading with time or with effective stress? And what are the different aspects of an odometer that we can vary? Perhaps, what does it mean to have single versus double drainage? So these are very simple concepts. Shouldn't be too perplexing for you because you have, well, passed the soil mechanics class, right? And then, taking a step further with the odometer test reading, some key concepts I want you to review. Evidently, we have to understand what is OCR. What does this ratio mean? To understand this ratio, you have to, of course, understand what the pre-consolidation pressure is. And we have, of course, discussed a graphical approach to find the pre-consolidation pressure, if you remember. Can you pull off the pre-consolidation pressure using this approach? What does it mean when a soil is heavily over-consolidated? What does it mean when it's normally consolidated? Where are you on the graph for both scenarios? How do we estimate the compression index and the swelling index? So CC and CS. What are their physical meanings? We always talk about physical meaning because that's the best way to grasp the concept. It refers to their stiffness, if you remember. How do we predict secondary consolidation? We talked about what type of graph we need, because with secondary compression, we're having constant effective stress. We're completed in terms of primary consolidation. There's no more excess pore pressure. So what's happening to the soil? Why is it still settling, right? Just like some of your questions that you asked me in your emails, what are we worried about after reclamation? Well, we're worried about residual settlement. We're really worried about secondary compression. When you hand over a site to your client, you have to tell them, okay, for the next 15 years, you will expect, let's say 150 millimeters of residual settlement. There's not much you can do engineer-wise, right? Because this is the deformation caused by changes in soil fabric. Also, how do we estimate compression? The magnitude. And of course, to do that, you have to look at the three equations at the bottom left. Under what scenarios do you use these three equations? Of course, it's well defined in your slides, but during exam, I might not tell you which circumstance to use each equation. Although you're given the equations, you have to make sure you understand the stress path. So this forces you to understand the concepts better, rather than just to employ an equation, because the equations are given to you. And of course, you have to understand what each variable means, and not just remember the equation. That's perhaps more important than remembering the equation. So know how to navigate this graph inside out, because you'll be given conceptual questions of consolidation. And if we ask you how much settlement do you expect at this effective stress at the end of primary consolidation, then you should be able to pinpoint that magnitude quite easily. The next topic we looked at in consolidation is related to rates. Up to this point in the module, we didn't talk about time. If we did talk about time, we gave you the time. In this case here, there are two types of rates. Rates pertaining to consolidation at a particular depth, so that's everything on the left side, and also rates pertaining to an average consolidation, not a particular depth on the right-hand side of the slide. So of course, any of these equations will be given to you, but the question is, do you understand the physical meaning of each variable? Right? If we don't define the variables for you, do you still remember what each variable means? That's a lot more important than remembering the equation. Remember that again. Of course, if you need, we'll give you any graph or table to complete any consolidation related question. But do you know what circumstance to use that graph? What assumptions were required to come up with that graph? So if we list a few assumptions where the graph doesn't work, then you have to be able to identify that. So that's why at the bottom of the slide, I stress what assumptions were made in the derivation of the above mentioned equations and graphs. Also, we mentioned log of time method, so make sure you know how to use log of time method. I can give you all the equations, but what is the log of time trying to calculate? If you don't remember that, then you may not understand what the question is asking. So anything related to how long it'll take to reclaim a piece of land, how long do you think it'll take before primary consolidation is over, how long will it take before primary and secondary consolidation is over, would be very normal questions to ask for rates related consolidation questions. So please review this part of the module. And after we talked about consolidation, we jumped off to a new topic called preloading. And if you remember, there are two types of preloading. There was surcharge field preloading, and of course, there was vacuum preloading. Surcharge field preloading is the module where we talked about PVD drains. Now, PVD drains are quite commonly used in Hong Kong. So we also did a calculation question together using PVD drains. So if I were to ask you, can you calculate the consolidation of this plot of land with and without the use of PVD drains? You should be able to do that, right? And if I said, okay, these drains, or this design considers the effects of smear, or doesn't consider the effects of smear, you should be able to do that as well. Of course, all equations, again, as I mentioned, will be provided for you. But some things that you really need to understand is, if I give you these two equivalent diameters, do you remember what they're for? Which pattern? Is there a triangular pattern? Is it a square pattern? So some of these things you have to really go through. Otherwise, even if we give you the equations, you may not be able to use them or recognize them. Or if we give you too many equations, you might get confused to use something else. And sometimes the questions may give you more data and information than you need. So you might not want to be misleaded by the question. So you have to understand the physical meaning of each expression. So in terms of preloading, you need to understand the process of field surcharge preloading, explain it in terms of soil mechanics, stress paths. That's quite easy to do, right? Because we're just trying to change the stiffness of the soil to minimize compression. For vacuum preloading, it's more of an experience-based preloading method, but we did compare the fundamental stress paths between field surcharge preloading and vacuum surcharge preloading. What are the differences in terms of stress paths? What's the difference in terms of potential failure mechanisms that we should worry about if we adopted field surcharge preloading versus vacuum surcharge preloading? And on the right of the slide, you can see that there are expressions there. U subscript R is for radial consolidation. So do you remember from our example of how we combined vertical consolidation with radial consolidation? If I give you all the information you need that you shouldn't have to memorize, can you use these formula to calculate the combined effects of radial and vertical consolidation? And if I give you both sets of equation for radial consolidation with and without smear effects, do you know how to use both sets of equations? Can you explain conceptually what smear effects are and also what well resistance is? Do you understand the range and the physical meaning of each parameter in those equations? So that's what you need to know for preloading. And then we moved on to the next topic of essentially over-excavation replacement, and we somehow broke this up into two types. The first one was shallow replacement, and the latter part was deep replacement. So in shallow replacement, if I give you a generalized ultimate bearing capacity equation and all the bearing capacity factors, shape, depth factors, can you calculate the generalized bearing capacity? And if I were to give you a question where you have to design for over-excavation replacement for the simplest mechanism, general bearing capacity, which is the first one in the red box, you should be able to tell me what depth we need to replace. And if I give you the properties of the fill material and the properties of the in-situ soil, you should be able to tell me whether an existing design is safe, whether we need to do replacement, if we need to do replacement, how deep. Now, we did talk about other methods of replacement, failure modes, for example, punching failure, and so forth. I'm not going to cover punching failure on examination because I think it's a little too complex and empirical, but conceptually, I still want you to understand the four modes. What are the differences? Can you explain the mechanism, at least concept-wise? over excavation replacement for shallow conditions is one of the forms of ground improvement. So when should we use this method? What are the suitable applications geotechnically that we can use shallow over excavation and replacement? And what are design procedures that we need to worry about? For example, do we need to check if we will fail the in situ soil by applying a load over first? So there are different steps, if you remember, that we check for. Do we check for short-term and long-term conditions? So procedurally, you should at least understand the calculation approach for generalized bearing capacity failure for over excavation replacement. But the other three modes are quite complex, so you can place less attention on those three modes. For over excavation replacement, we treated that as shallow replacement, and then we transitioned into deep replacement. For deep replacement, these approaches are highly experience-based, highly empirical, but we did spend some time to talk about what's the difference between excavation approaches, displacement approaches, dry, wet feeding from bottom and from top. What are the differences conceptually? And if you look at this schematic at the top, we did talk about under what type of soil conditions each approach is suitable. So if you look at these approaches, can you tell me whether we should use this in clay, should we use it in sand? So you should be able to at least identify a suitable range of soil conditions for each type of method. Also, we should be able to discern the advantages and disadvantages of each deep replacement method. So this module would more be conceptual based, right? And again, when you're studying, you could probably guess a lot of these things. What's more conceptual based, what's more calculation based. So the consolidation module will probably be quite calculation heavy, right? Whereas some of these approaches where we didn't do calculations together were conceptual based. So this should be the approach you take when you study. Also, we talked about what geotechnical applications would be suitable for various types of deep replacement. So if I give you a scenario and I ask you to recommend a form of deep replacement based on a series of prior conditions, you should be able to recommend the most suitable. Or if I give you three options, you should be able to give the most pertinent one as well. So in order to do that, you must understand what's going on with each approach. So that's generally all I would like you to review on deep replacement. And we have drainage, dewatering, drainage spilled incorrectly, and geosynthetics. So this module was also conceptual. We didn't spend a substantial amount of time trying to calculate and design a dewatering system in the ground using deep wells and sump pumps, but we did spend some time talking about what geotechnical applications we should use, dewatering, drainage, and geosynthetics. We also spent some time trying to differentiate among the different types of geosynthetics, what they're used for. We talked about different geotechnical applications where dewatering is used, such as cofferdams, pumping test. So this module again would be quite conceptual. If I give you a scenario where I want to have erosion protection, for example, or I want reinforcement, separation, then you can perhaps conceptually propose a suitable solution. And you may have noticed that geosynthetics were used quite a bit in other types of ground treatments, such as encased replacement columns. We use geosynthetics just to wrap our PVDs as well. So if you can spot linkages among the different types of modules that we've covered, then that would be useful as well. If you see the little table at the bottom left, we talked about under which circumstance a particular type of geosynthetic would be useful. So you should understand that. And for dewatering at the top, we spent quite a bit of time talking about grout curtains, applications for dewatering, implications for pumping tests. So conceptually, you should understand that. And on the right, we show a series of application where we have drainage being used. So you can list some of these applications, or list some of the applications where geosynthetics, drainage and water may not be usable, or may cause practical problems that would be helpful as well. Nearing the end of our course, we talked about grouting and deep mixing. So these are what we call chemical ground improvement approaches. For grouting, we talked about permeation grouting, compaction grouting, soil fracture grouting, jet column grouting. So among these various approaches, when should we use them? If I give you typical soil conditions, as you would see on the right of the slide here in the table, can you identify which approach we should use or which approach we shouldn't use? Which approach would be the most feasible or cost-effective under a certain situation? I mean, of course, we have conditions where we can use, for example, compaction grouting, but it may not be the most optimal range to use for that type of soil. Do you understand the procedures for permeation, compaction, soil fracture grouting? Under what geotechnical applications are these most favorable for? What do we consider in a grout design? Do we care about its rheology, particle size, groutability? What are some factors that we worry about? Are we worried about the overburden pressure, injection pressure? And as we're doing grouting, what type of machines do we use? Equipments do we use? What do we monitor? Injection volume, injection pressure, grout volume. So these are all concepts you should be aware of with anything related to grouting. We also talked about TAM pipe. Why do we use a TAM pipe? How can we use a TAM pipe, for example, for soil fracture grouting? Why do we use it? What kind of control do we have? So anything related to application, ideal soil conditions, and methodology of grout injection method, you should be able to explain conceptually. Of course, we didn't do any calculation questions with grouting, so you would understand conceptually what the different types of grouting methods are. It's probably ideal enough for this examination. The last topic we covered in our course was deep mixing. Now, in deep mixing, we talked about wet deep mixing and dry deep mixing. The only fundamental differences are the type of binder injected, whether it's powder or slurry, and of course, there's slight differences in the construction sequence. And we talked about what type of deep mixing we used in Hong Kong for the third runway system, and why we did that, and what are the disadvantages of using wet deep mixing. So based on our discussion in our course, you should be able to reveal the advantages and disadvantages of deep mixing using various techniques, the applications most suitable for deep mixing. Some case studies that we discussed related to deep mixing in Hong Kong, you should have an idea of how we applied it in Hong Kong. Because what if I asked, what are potential ways to improve existing practice in deep mixing? Where do you see potential improvements? If you understand conceptually what's going on, then at least you can answer those concept questions. So not too complex here, mostly, again, conceptual items you need to worry about for deep mixing. And we talked about in situ testing. Near the end of today's lecture, I'll go through two quick examples of in situ testing with you. Why do we do in situ testing? Would you consider sand replacement in situ testing for shallow compaction? When would we use SPT or CPT, right? These are the two main types of approaches we covered. We didn't cover DMT, PMT, or VST. We covered SPT and CPT, but these are among the various types of in situ testing. And why do we do in situ testing? Why do we rely on so much for ground improvement? And we talked about these concepts, and particularly SPT and CPT testing. What are the procedures? These are so commonly used in Hong Kong that we should understand these two topics: how to calculate the end flow count, how to calculate and correct SPT, corrected values. If we look at CPT data and I give you all the equations you need, you should be able to interpret the CPT, SPT data sets, right? So key concepts to review for in situ testing. What are the standard methods or the test procedures for SPT and CPT? What do we gain from doing SPT? For example, with a split spoon, we can get some highly disturbed samples. CPT, you're not going to get any samples, but you'll get continuous profiles. So there are obvious advantages and disadvantages with each type. SPT data is somehow difficult to interpret. Depends on what cutoff values or termination criteria you're given. And let's look at two examples, one of SPT and CPT near the end of today's lecture. It's quite simple, it's not complex, especially if you're given all the formula. So in summary, I tried to cover the concepts in terms of modules, but I mentioned already that you should have some holistic sense as to how to link the modules together, because we talked about for a given site, we don't just use one type of ground improvement for a land reclamation project. We use PVD drains concurrently with fill surcharge preloading, for example. We may also do water. So try to link among the different modules and see if there are any synergies among the modules. As we mentioned continuously throughout the review, we really have to know when we use a particular type of method and what are the pros and cons of each method. If I give you a scenario for a particular ground condition, can you recommend what geotechnical ground improvement technique to use and what should be the subsequent quality control or quality assurance measure? And if you're able to link the modules together, there's a short concept question on how you can improve the existing state of the art, then perhaps you can propose some innovations, some hybrid approaches based on your understanding of the modules. So conceptually and I guess calculation-wise, that's all I want to talk about for the review. Some of these were a little too obvious, as you'll see on the exam, but I hope this helps. So to end this course, I wanted to just cover two examples with you, SPT and CPT. So if you were to see an SPT related question, one type of question would be how to interpret a table of SPT data. So we went through that example together in class. A second type of question is, well, how do you correct for SPT values? So in this example here, you're given the soil geological model, you're told depth, then you're told the flow counts, the measured borehole diameter, the measured penetration increments. You're using a standard sampler, and you're given the length of the rod. Now, and then you're asked to calculate the corrected SPT value for a particular penetration. And of course, you're given the geological conditions simply by saying that the water table is 2 meters below the ground surface and you're given the unit weight. So how do you get the corrected SPT value? Well, if you remember from our course, I give you this slide, which has all the equations for SPT correction, and you would get all these equations on the back sheet of your exam anyways, for the various types of corrections and conditions. So we remember that there are 4 types of corrections, right? We have hammer efficiency, we have effective stress, we have borehole diameter, and we have rod length. So this was in your notes, right? So if you want to calculate a corrected SPT value, you would just look at each of these corrections. So rod length 8.2, you know that you should use 75%, right? Under A. Corrected overburden pressure, you'll be given the expression Cn. You can calculate C subscript n is 1.18. On the top right of the slide here, you have the ground profile if you need to draw it out. You have the correction for borehole diameter given as 150. So we know that for a 150 diameter, we are given a correction factor of 1.05. Rod length 8.2. If you go back to the slide, for rod length you're also given the recommended correction factors for C subscript R here. That's why we use 0.95. And to correct the SPT, it's quite easy. First of all, you have to know what your non-corrected n is. So based on the data, we know that our non-corrected n is corrected by multiplying by 4 of these correction factors, and you'll get 15 flows per 300 millimeters for medium sand. So we may try to confuse you and say, for the seating drive, we got this penetration, and you should know that we don't really count the seating drive, right? If you remember from our examples together, so don't be confused by that. So it's quite straightforward if you do the concepts for SPT. And this is, well, as complex as SPT related questions can be. Second type of question you could see is related to CPT. So you're given a table of CPT data, you're given that the groundwater table is 3 meters below the ground surface, and you're given dry and saturated unit weight of the soil. And you're asked to do 3 things. What type of soil is at a particular depth? Estimate the undrained shear strength at 5.5, and you're given the cone factor. Estimate the shearing resistance, essentially phi dash, at 7.5 meters. Now, again, all of this information shown on the slide would be given to you on the equation sheet. The question is, do you remember what each of these variables are? So we have total cone resistance, we have net cone resistance, we have QS, which is the ratio of shear force over area, we have friction ratio, we have sleeve friction resistance, and then we have these 3 values here. So we can give you all of these expressions. And what else can we give you? Well, we can also give you, well, you also get cone area ratio if you need. We'll also give you, besides solution, we can give you any table here. We can give you this graph. And if you remember in the first question, part A, the groundwater table is 3 meters below the water table. We're having 2 different unit weights. You're given this expression, so you calculate the corrected cone resistance. But the key trick here is to be able to differentiate in the expression when to use total and when to use effective stress. So we give you a table of different depths, and you would calculate the different parameters using the same expressions you see here, and you can tabulate it. So you're given total stress here for the calculation, you're given effective stress, pour water pressure, you can calculate for different Z's, and you can calculate cone friction ratio like this. So all these expressions are given in your exam. Now the question is, what do you do with it? Well, to identify the type of soil, we would give you some graph as you see on the right, and what you would do is tabulate it. So all those equations I gave you, you can tabulate it. And obviously we won't give you 20 depths to calculate. And can you use these variables here? So if you look at here, what do you need? You need normalized cone resistance, you need normalized friction ratio, and you can identify what type of soil by using this table here. So based on that, can you write down what type of soil classification you see based on that table? And also, other parts of the question ask for what's the undrained shear strength? Well, this is also from your slides. You can calculate the cone resistance to get the undrained shear strength if you know the cone factor Nk, and we gave you the cone factor in the question. So this is not additional information. This slide is directly from your notes on CPT. This is also directly from your notes. If you know your cone resistance and you know your vertical effective stress, then you can pull off phi dash. So based on what you know from your notes, you can calculate the undrained shear strength. So just don't get confused, right? If you don't see a dash, it's not a mistake, then the equation must be in total stress. You're given Nk as 18 in the question. For a particular depth, 5.5 from the table before, you can see that you're given QC and you're given total stress. So you can calculate the undrained shear strength as 16.7 kPa. And to find the phi dash, well, you can just use this method here. So find the cone resistance, you calculate the vertical effective stress, you can pull it off this table here, and based on Robertson and Campanella, you get 41 degrees for phi dash. There was another graph in your notes from, I think it's Paul Meany. He 2006, and that would give you 39 degrees. So anything related to CPT and SPT, we will give you all the equations and graphs that you'll need to extrapolate. The key is just to form a table where you can pull off all data at any particular depth, and you can plot any graph you need, and that's how you would solve these type of questions. So they're not too complex, and that's all I want to talk about for the review. So I've posted these onto Moodle, including the CPT and SPT. And if you have any questions, feel free to email me, or we can Zoom before your exam. Or you can contact me on your TAs. I think they uploaded all your grades for your assignments. I think you more or less have all the grades you need going into the exam, and I don't think the exam this year is too complicated. So good luck, and yeah, I'll see you on the 12th.